Hello, trigonometry students. Since our connectivity has been so bad on Cisco WebEx, I've decided to pre-record a bunch of lectures in hopes this will help you. All right, so going past graphing trig functions and solving a few elementary baby trig equations, which we've been doing, we move on into chapter 5, where we prove more trigonometric identities. Okay, so trigonometric identities, statements that are true no matter what the variable value is allowed to be, come in 3 batches in this course. Early on, we had a bunch of identities coming out of our definition of the unit circle, and definition of cosine and sine as the x and y coordinates of p sub theta when theta is drawn in standard position on the unit circle. And from that, we had gained a bunch of fundamental trig identities. Let me remind you of what those looked like. So from this picture of the unit circle, if we put an angle theta in standard position here was p sub theta, q sub theta, and O for the origin, R, which was fixed at 1, 0, S sub theta, which was, if you draw the tangential line, tangent at R to the unit circle, and where it intersects the terminal ray of theta, we call that S sub theta. And we, from this, generated 2 right triangles, OPQ and OSR. Also, we hadn't done it on the same picture before, but you could do it on the same picture. Identify here is the complement of theta. So here's theta prime, the complement. They add up to 90 degrees, or pi over 2. On the triangle OTU, we use that to define some functions in terms of theta prime. Also, the triangle, these triangles OPQ, OSR, and UOT are all similar to each other. Okay. Notice that in the triangle OPQ, we had theta here, theta prime over here. In the triangle OUT, we have theta prime here, but theta, its complement, way out here. So we got a bunch of identities out of this. And again, we didn't look at it in quite this fashion before. Maybe not so prettily drawn up as what I had been doing for you live in class before. But those triangles, OUT, POQ, SOR, are all similar, right? And their sides, because these are, the angle theta is acute, the lengths of the sides of the triangle OPQ could be identified with the sine of theta and the cosine of theta. The triangle OSR had sides 1, legs 1, and tangent of theta, the hypotenuse being the secant of theta. And the triangle OUT had sides whose lengths we find to be the cotangent of theta between UT and the cosecant of theta between OU, and OT, just because it was a radius of the unit circle, was equal to 1. So from each of these, we got a bunch of relations. First of all, just from Pythagorean theorem, which I could ask you guys to fill in the blanks why these things are true. But going from here to here, that's just the Pythagorean theorem. Let's see, what else do we have? over here with OUT, notice that the cotangent of theta is equal to, the cotangent of theta is to 1, as the cosine of theta is equal to the sine of theta. Your book refers to this as a trig identity. We call it its definition, and extend this as the definition even outside of, for theta, outside of quadrant 1. The cosecant of theta was to 1 as 1 was to the sine. The tangent of theta was to 1 as the sine was to the cosine. The secant of theta was to 1 as 1 was over the cosine. So these all became our definitions of these 6 trig functions. Again, your book thinks of these as trig identities, the fundamental ones. Applying the Pythagorean theorem to this triangle gives us cotangent of theta squared plus 1 equal to the cosecant squared. Applying the Pythagorean theorem to this one gives us 1 squared plus a tangent squared is equal to secant squared. Can't tell you how many times I've used this identity in Calc 2 just this past month. Comes up a lot. This one always was coming up, even in Calc 1. But later on, you get to use these guys in the middle of an integration problem in Calc 2. So it's nice to see that these 3 triangles, you could actually, because they all have this angle theta common, you can embed them one inside the other. And taking that and their labels over here, we get a nice little diagram here, which I like to show you just so that you have an idea about the sizes of these functions. So notice that the cosine and the sine would never be greater than 1 because they are legs of a right triangle for which 1 is the hypotenuse, the largest side, right? But you'll notice that the tangent of theta here, it's part of this triangle OSR. In that case, the distance from here to here is called the secant of theta, and the distance from O to R is 1. So this just gives you, for this particular choice of theta, the kind of relative placement of the different functions. Finally, on OTU, we have this hypotenuse is the cosecant, the base is of length 1, and this long leg is the cotangent. It makes a nice picture. Might help you. But in any case, those are what we call our fundamental identities. So of the 3 batches of trig identities that you're coming up against, you've already had this first batch, the fundamental identities, for a long time. Secondarily, we have a set of about 17 identities, which I'm going to derive in this video, start deriving in this video and finish in the next. And it comes from deriving an identity about the cosine of the difference of 2 angles. That's where I'm going to go today. The third batch, just to give you an overview, is going to come from a bunch of trig identities that you're going to see in Chapter 5, which are really presented more as suggested identities, and you have to prove them using logic, arithmetic, algebra, and the previous identities that you had before. So you're going to create a lot of these identities, or you're going to prove a lot of these identities. These others get used so often, especially these 17 identities in here that we're about to derive in this video and in the next one. They occur so often in calculus that you'll get to know them pretty well, or at least, I hope, learn how to derive them, which is really all that one can hope to do, instead of just memorizing them without understanding. Okay, so let's begin with the cosine of a minus b. The claim is that the cosine of a minus b, well, it's not the cosine of a minus the cosine of b. okay? You could prove that that's false if you had the feeling that it's cosine of A minus cosine of B. Oh, just try it with A equal to pi over 2 and B equal to pi over 6, okay? Pi over 2 minus pi over 6 is a pi over 3, right? The cosine of pi over 2 is 0. The cosine of pi over 6 is a half. Square root of 3 over 2, sorry. 0 minus square root of 3 over 2 is a negative quantity. For 1, if you took the cosine, if you thought that was equal to the cosine of pi over 2, 0, minus the cosine of pi over 6, excuse me, we already worked that part out. I'm tired. But if you just look at A minus B, where A is pi over 2 and B is pi over 6, their difference is pi over 3. What's the cosine of pi over 3? 1/2. Is 1/2 equal to a negative square root of 3 over 2? It is not. So make sure that you catch yourself from making silly errors, like assuming that you could just distribute the cosine through this. Completely false, okay? Instead, we have this interesting relationship, okay? This is what we're about to prove is the case. So the cosine of the difference of two angles depends on those angles' cosines and sines for both angles in this very peculiar combination. How did they get this? So we start by imagining if we want to talk about an angle cosine of A minus B, we want that difference to be a positive angle so we can look at it. We make A significantly larger than B. So let's say that this is our angle A, and we put that in standard position. Notice that at these endpoints here we have R, the point 1, 0, and up here, this is where A is terminating, so that's the point on the unit circle where this terminal ray intersects the unit circle. Its coordinates by definition are the cosine of A and the sine of A, or whatever its coordinates are, we call the x-coordinate the cosine of that angle and the y-coordinate the sine of that angle, right? If B is a much smaller angle, and we put it in standard position, where it terminates is at the point PB, and whose coordinates, x and y coordinates, get called cosine of B and sine of B, right? So now I want you to focus on the angle, which is the difference between these two. So A went all the way over here, B came just up to here. The difference between those two is represented by this angle here. Okay? So notice how this point is at PB and this point is at PA. Okay? And in fact, if I took that angle A minus B, which has yet to be put in standard position, but if I just rotate that around there for a minute and draw the line segment from that point to that point, look where we end up. So let's see now. So this purple angle here was representing the angle A minus B. There it is, A minus B. And if we draw the line segment from PB to PA and call its distance D, right? And now let's put A minus B in standard position. So here's my angle A minus B in standard position, right? With its initial ray over here on the positive x-axis. Where its terminal ray intersects the unit circle is a point called P sub A minus B. That's the angle, which is the difference of angle A and angle B. And so therefore, of course, its x and y coordinates get called the cosine of the angle A minus B and the sine of the angle A minus B. Notice that this distance that was between PA and PB is the same as the distance between P sub A minus B and R. Same piece of paper. If you rotate this thing, that does not change the length of that line segment. So the distance between PA and PB is the same as the distance between P sub A minus B and R. And you remember your distance formula. To find the distance between 2 points, you subtract their x-coordinates and square those, subtract their y-coordinates and square those, and then add that together and take a square root. Same thing over here when you're finding the distance between this point and this point. It's that x-coordinate minus this x-coordinate, the quantity squared, plus that y-coordinate minus this y-coordinate, the quantity squared. Add those two together, take the square root, and you've got that same distance d. So the distance d here, in one aspect, can be represented this way. If we rotate it, it can be represented this way. So also notice that these two distances, you could say this one is d1 and this one's d2, for example, they're equal, so therefore their squares are equal. And so then I get to square both sides of this and get rid of those the square root symbols. That's nice. And now I just have a sum of squares over here and a sum of squares over here. Well, a difference squared, cosine A minus cosine B, is cosine squared of A minus 2 times cosine A cosine B plus the cosine squared of B. Plus the sine of A minus sine of B. If I square that out, I get this one squared, that one squared, minus 2 times their product. On the right-hand side, if I square out this difference, that's the cosine of A minus B, that's one thing. Minus 1, that's the other thing. If we square that, we get this one squared, minus 2 times their product, and plus 1 for the 1 being squared, plus this sine squared. Right, sine of A minus B minus 0 is the same, and then squaring that is the same thing as just talking about sine squared of A minus B. So now we can group a cosine squared of an angle A plus a sine squared of an angle A and get the number 1. Similarly with the cosine squared of B, if we add it to the sine squared of B, the same angle, we get another number 1. Cosine squared of A minus B added to the sine squared of A minus B. The identity about the cosine squared plus the sine squared equaling 1 is true for any angle. So that gives us another 1. So we've got 2 minus 2 times this stuff. How do we get that? We put these two down here, added them, but then factored out a negative 2. So we've got this 1 and this 1, which we're going to add together to get a 2, minus this remainder over here, minus 2 times the cosine of, oh, looky there, A minus B. So now we have an equation with a 2 minus 2 times something equal to a 2 minus 2 times something else. So let's subtract the 2's from both sides. These 2's, those cancel. Now let's divide through by a negative 2 on both sides. Those cancel, and we're left with our result. That the cosine of the difference of two angles is not the cosine of A minus the cosine of B, but rather it's the product of their cosines added to the product of their sines. That was our claim, and so that proof is done. And I will make that the end of this video. And in the next video, I will show you about 16 identities that fall out of this one, plus a little help from another set of identities. Okay, next video.